is Anatol Prisacaru, or as some of you know me, Sharkcoder. And my presentation today is about hacking Ethereum smart contracts. First of all, who am I? I'm the founder of a community called Security Espresso. It's mostly about security, like you have the DEFCON groups, we have Security Espresso here in Romania. I'm a security researcher. I dabble with web, Linux, mobile, and blockchain as of a few years. I started as a developer. My first language was actually back in high school, was Visual Basic, then I learned Pascal, then I coded a lot in PHP, but right now I code in Node.js, Solidity, or literally anything that does the job. I spoke at a few conferences. Can you hear me? Okay, I think I heard my own voice. Okay, so I spoke at a few conferences. Definitely, I was a speaker at Volga last year, so I'm happy to present this year as well. Also, I'm a co-organizer of the DevCamp conference here in Romania. Maybe you've heard of it. In the DevCamp, we have DCTF, where I'm usually responsible for all the infrastructure. We have a Wayfound Poundboard. Maybe you'll know it by another name, it's Wolf Ship. And I started I put the basics for the Hack the Bank competition that we have at DevCamp. And of course, I'm a coffee addict, so I love the coffee, hence the community name is Security Espresso as well. Good, so we're gonna talk about blockchain, but what is that? So maybe it's not the first time you hear about blockchain, and maybe you saw this image on the internet. Basically, a blockchain is a chain of blocks. That's the basic of it. And to give you a better understanding of what a blockchain is, think of it as a decentralized ledger. That means that there's a book with records in it, like who owns how many money, who has how much money, and it's a list of everyone that has some money, and it's stored in a decentralized way. Everyone has this list, and anytime there's a change to it, and anyone will have the update. So that's the definition of a blockchain per se. There are many blockchains out there. The first one was, of course, Bitcoin, and then hundreds, if not thousands of them appeared. And as of 5 or 6 years already, we have seen that there was innovation in the domain, and we saw Ethereum being born. Ethereum, compared to blockchain, has much faster block mining, 15 seconds or 12 in average, compared to Bitcoin, which has in average 10 minutes. It's a platform for smart contract, and that's the important part, and we'll be discussing this a bit later. It has a few standards. One of them is ERC20, which is a token standard, and basically you can track assets on the blockchain. So what the hell are smart contracts? First of all, Ethereum is a programmable blockchain. So you have a language, be it Solidity, Viper, or Yule, and you can write code that will execute on the blockchain and will do custom logic instead of just sending value from one peer to another. A contract means basically an address and some code. Contracts are basically objects. Like you define a class that's in your code, and then you deploy it to the blockchain, and it's an object of that class. That's basically what a smart contract is. The blockchain itself acts as a database or as a storage, and you can write to it or read from it, and anyone can execute any existing code on the blockchain. For example, if someone deployed a smart contract, anyone can call it and run some code from it. So basically, it's a globally accessible API, and everyone is free to call it. And the miners that you know, for example, from Bitcoin, they are actually running EVM code, Ethereum Virtual Machine bytecode. that's generated by the language that you wrote your smart contract in. So I hope so far we're good and you understand this. A simple example of smart contract would be this one. For example, we have a counter contract, basically a class. It will have, first of all, when it's deployed, it has an address where you can, which you can use to interact with it. Every smart contract is similar to an usual address that doesn't have code, and it has a balance. Then the new part that a simple address, a simple wallet doesn't have is the code and the state. The code itself is the one that you write, and the state is the storage that I was telling you earlier. Basically, the database of the contract, or however you want to name it. So this is a simple example, a counter. It has a slightly older syntax because we have a constructor here with the same name as the contract name. Nowadays, we have the constructor keyword for that. But when it's deployed, it initializes the counter to 0, and then we have a public count function that everyone is able to call, and it will increment the counter stored in the contract by 1. Okay, moving on. EVM bytecode looks pretty similar to assembly, somewhat. It has a stack, it has some memory, and basically the instructions tell the virtual machine what to do with the memory and how to manipulate it to have the functionality that people want. I have here for a contract that I filed and used MyThrill to generate it, and you can see that it has jumps, it has different functions, and the control flow graph might help you debug contracts that you don't have the source code of. There are more advanced decompilers as of today, and you can find a few of them online, and they can generate some code, not necessarily recompilable code, but something that you can understand what's going on and use that to analyze the contract itself. Okay, moving on. Having code on the blockchain means that usually people say that code is low in this domain. Oh my God. Usually people say that code is low. So having something on the blockchain that is low and is defined by code means that we'll have, of course, some bugs. Some classical vulnerabilities are the following. First of all, we have the classical reentrancy vulnerability. Afterwards, we have the randomness source. That's an issue in this area. We have some fallacies regarding the private variables that we have in the contract. We have issues with, especially in Solidity. I'm not aware how this is taken care of in Viper, for example, but we have issues with initialized storage that sometimes we might accidentally write to. There's the short address attack or address truncation and others. We will explore a few of them and a few security incidents that happened along the time. The first very big security incident was a DAO hack. It's already been a few years since that, but it was one of the biggest, and the attacker managed to steal 150 millions of dollars. Then we have two Parity problems that we exploited. The first one resulted in 30 million loss, and the other one in 155 millions. This February this year, we had two exploits. That's actually the same exploit, but exploited in a matter of a few days. Back in February, on 14th of February, it was a Friday, the first exploit happened, and then the developers paused the contracts, investigated, said everything is good, and they didn't consider this a hack. They resumed the contracts, and a second hack happened. Basically, the attacker was able to steal around $1 million at that time. This year as well happened the length.me exploit, the hack, where the attacker managed to steal different funds, not only Ether, not only one asset, but multiple, and the approximate amount of the loss was 25 million. And just a few days ago, like this weekend, happened the third BZX exploit. And at first, it was believed that the attacker managed to steal only $500,000, and the dev team said that they will reimburse this amount from the insurance fund. Afterwards, it was discovered that actually the attack was ongoing for a few days or maybe even weeks, and the total lost amount was 8 million. Okay. So to explain the first DAO hack reentrancy vulnerability, I'll show you a simple contract. It's not a simple function. It's not the actual code that caused the actual hack, but it's really similar and much simpler to understand. Basically, there was if we have a withdraw function, and anyone can call it. First of all, in the function, we see that the code is checking whether the sender, the one who is calling this function, has enough balance to withdraw. Afterwards, the contract sends the amount requested to the sender, and then decreases the balance of the sender. The problem is that in the line where the amount is sent back sent to the message sender, the attacker is able to call this function recursively. So basically, he will enter the function again, and the check will happen again because nothing has changed in the balances state in the variable. So he can call this function multiple times, and then when called again with some money and he doesn't call this again, all the balance will be subtracted for every call, but the attacker already has the money. So the lesson learned here is that, first of all, when you're using message sender call, especially with a value, it's good to know that the destination can be a contract, and it can call this function again or other contracts in the system. Second, use a pattern checks, effects, and then action, where you first check if this action is allowed, then you do the effects, which means you subtract the balance, and afterwards you do the action that send the actual money to the requester. Okay, moving on. The parity was a simple one. First of all, they have a wallet library, and the wallet library had an init wallet function. Libraries in Solidity are similar to the libraries that we use to install from npm, or we using pip in Python and so on. So basically, it's some code that you add to your project, and then you can use it. The problem was that in the wallet contract itself, the wallet library was called using a delegate call in the fallback function. Fallback function means a function without a name, and if there's a function call in this contract that doesn't match any function, the fallback function will be called instead. Sort of a wildcard function or a default function that will be called instead of if the target one is not found. Okay, so what happens here is that all the calls to the wallet that don't have a corresponding function will be passed to the library. So basically, anyone would call the library, would be able to call the library if there's no corresponding with the same name and parameters function in the wallet. So what the attacker did is to call the init wallet and set himself as an owner, and then he was able to drain all the funds. The second attack was kind of a funny one, so a lot of people remember it and laugh about it. It was actually an accident, to say so, because someone found the function and called it, and what the function actually did was to kill the contract. Killing in Ethereum means destroying the object, so basically killing all the functionality of the contract. After destruction, the funds are sent somewhere, usually to the one that called kill, or depending on depends on how the contract was implemented, it can be sent anywhere or not sent at all. Okay, so what DevOps 199 did is he called the function by accident and then posted on GitHub that opened an issue on GitHub and said that anyone can kill the contract, and that he accidentally killed it, and added the link to the TX that killed the contract. What happened is that Parity had this kill function that would destroy the contract, but they would have a modifier which is a check, or it's a middleware to say from other languages, that would check that the call is allowed, but they forgot to initialize the owners of this contract. So basically, he was able to kill this contract, and a lot of funds got lost, and basically nobody stole the money, but nobody was able to benefit from it. Burned money. That's what happened. Moving on, we have the third BZX hack. I'll show you the details of the first and second one later on, because I'll cover some basics before getting to that. But the third BZX hack that happened like 2 days ago was because wasn't because of a standard solidity vulnerability, but rather was some logic in the code. And in a special scenario when the attacker would have exactly the same amount of money that would he if the balance of the attacker would have the same money to some other variable, I can't remember right now exactly what it was, but you can follow this guy on Anton Bukov on Twitter and see his explanation this. But this was the fix, basically, moving two variables at the top because afterwards they were modified and those weren't correct anymore. Okay, besides hacks that happened, there are a few cases when, actually a lot of cases when white hackers called out on developers and told them, like, look, there's a vulnerability, you should take care of that. For example, this one is from 2017 in December, when Razer, if I'm not mistaken, he might be Russian, So this guy was looking at the Ethereum lottery, and he said, like, look, developers, there's a problem because anyone can predict the outcome, and you can basically win the lottery continuously. So he posted this issue, and then the developer said, look, you don't understand it. It's not possible. If you want to place a bet, someone will to place a bet and calculate the number that will be the outcome. Someone might be faster than you, and the number will change, and you will not be able to win this. And if you're so sure that you can win this, there's a jackpot of $200. So prove us that you indeed are able to hack this. So he went ahead and wrote a simple contract that won the lottery. So he proved he won it. He took a screenshot and posted the outcome to the same issue. And it was an amazing moment. Everyone was watching this. Developer didn't understand his lesson from the first time. He did something else. He changed a bit. Razor then commented that this is not a fix. This is still hackable, and so on. But what we can learn from this is that the randomness, the source of randomness, is a problem in the smart contracts world. Okay, so this is basically the transaction, the winning transaction that Razor posted. Okay, so now we'll see a few contracts that are in the wild. For example, we have a Roulette contract that depends on a random number generation. What the developer attempted to do is take a few random numbers that are present in the the present block. It's not really random, but he considered that these are random enough. So he took the block number. Afterwards, he took the block difficulty, the block timestamp, the gas limit, added all this, and divided by got the remainder when dividing by 37. So similar to a roulette, from 0 to 36, and return this value. And he considered that this is random enough and hard to guess. But the problem is that anyone can write a similar contract and put the same numbers in there, and after and getting the result, and after calling with the outcome from his contract to win. So someone did that, and you can see that there are two TXs. You should read from bottom to the top. First, he sent 1 Ether and 136 Ethers, and repeated the procedure to win the other 36 Ethers. Basically, winning 2 times and draining the entire lottery out of money. Afterwards, we have some more interesting things in the wild. For example, there is this address lottery. It has 1 Ether in it, and it has verified source code on Etherscan as well. And if you would look at the force seed function, that's callable only by owner, and it's thought to be like an initializer. Basically, we have a seed components as variable or struct, as they're called in Solidity. Each component is assigned a value that's like in the previous example, believed to be random, like the block hash, the block number, the takes gas price, and the owner as well, but that's not already random. But the problem with this is it's not the randomness, but rather another issue. If you'd copy that code and put in and would use a checker, a code checker, then it will point out that on line 86, we have a variable that's not initialized. So basically, S would point to the slot number 0, and when assigning to component 1, 2, 3, and 4, it will actually override state variables instead of modifying the seed components as variable. So what this does is actually it creates what this contract actually is a honeypot, and makes you believe that you can hack it, but actually it will steal money from you. And in this example, we can see that there were 2 people that actually sent money to this contract and fell into the honeypot. There are more examples of this. For example, there's a contract that makes you think that you can just withdraw some Ether because there's a vulnerability and you can drain the entire contract. But the problem is that if you get this code and paste it in Sublime, you will see, hopefully you'd notice that there's a scroll bar. And usually if you have like 120 characters on a line, you shouldn't have a scroll bar. But if you scroll to the right, you'd see some additional code that the attacker didn't want you to see. And what the attacker does is send the money to himself instead of you in the withdraw function. And afterwards, Etherscan implemented line wrapping, and you can see that on line 4, the code is now visible because it got wrapped. Another example of a honeypot is Hodler Paradise. So at first, this contract was weird. I was looking through it. Basically, what it does, it allows you to put some money, and there's a 7 days lockup period that if there's someone that deposited money in this contract, the owner cannot kill it because of this check of last deposit time. And give this would in theory give you the guarantee that the owner wouldn't kill the contract and subtract the money. Looking at this contract, I noticed something weird, and this was this last hodler parameter sync. I was searching for it, and it was weird that some text would be highlighted by the editor when double clicking it, and some other similar strings wouldn't. So I did a search in the contract, and it just found one match, although there were a couple of them. So I knew that there's something weird with that parameter. So I put it in a file. I copied 2 of them and put it in a file. Then did the hex stamp of the first line and the second line. As you can see, first line and second line, these look identical, only look, because they aren't in fact. And you can see that the O letter from the first string is actually a double point, is actually 2 dots in the first example, and it's a normal O in the second example. That's the moment when I realized that O in the first example isn't actually O, but it's actually the letter Omicron, from the Greek alphabet. And as you can see, it looks exactly the same, at least with the font I was using. So yeah, with this, the attacker was able to, the attacker that constructed the honeypot was able to fool people that it actually has a lockup period, but it was bypassed using this clever technique, and he would just wait for someone to put money and then kill the contract and take all the money. Okay, moving on, we'll talk about centralized exchanges and decentralized exchanges. First of all, a lot of things happened in the past few years, and DeFi, decentralized finance, has grew a lot, and that's mostly because of the decentralized exchanges and the all the magic that happens behind them. In the centralized exchanges model, we have the exchanges that Binance or the Mt. Gox, if you remember from a few years ago. There's the Poloniex, there's the Kraken, and so on. And the exchanges control the funds. You have to deposit your funds. You don't have the private key for them. All the exchanges ask you for your ID, so you have to send your passport there in order to be able to withdraw your money. And in the decentralized world, the exchanges don't control user funds, so basically you don't have to deposit anything. You interact with it directly by using your wallet that you have the private key for, and they're anonymous, or at least pseudo-anonymous, because anyone can see the transactions, anyone can see what happened, but they don't know who is the person behind that. So the interface for a usual centralized exchange would be like this, while DEX would most likely look like this, or something similar, might be more complicated. This example is of the Uniswap exchange. Why is this why does it look so simple? It's because in the centralized model, everything happens every microsecond. There are hundreds, thousands of orders every second, and everything is not on a blockchain. So they can put a lot of servers, a lot of bandwidth, and serve a lot of customers. In the decentralized world, there's no anything like that. Everything is on-chain, and everything that happens through the chain, and nothing. Although there are a few hybrid exchanges, everybody relies on the blockchain for trust and all of that. Okay, so on a decentralized exchange, there are smart contracts, and for example, the Uniswap has a formula for the price, because on centralized model, you can set the price. As an exchange, you can set the price and fool people. In the decentralized world, everything is fully transparent, and you have the contract code, and you see the formula. And usually, for example, a lot of examples have the quadratic model, where the product of the amount of tokens should be the same. So you have, if you have quantity of B tokens in the pool high and quantity A of tokens in the pool low, that will mean that the price is very high. And if you move the other way around, and you have a lot of tokens A in the pool but low of B, the price of A token will be low in B tokens. So basically, this relies on someone to move in tokens or take out tokens by depositing the other one. And the price will be calculated automatically. Why is this working? Is because if we move the red point somewhere high enough, but all other exchanges have a different price, there will be an incentive for someone to come here and trade to have because they will have a better price. I hope I explained this well, but I understand this might be a bit difficult. You can read about this on the Uniswap documentation. But we'll consider this somewhat explained. Okay, so many of you might have heard of arbitrage. It's a technique where you have two exchanges. It doesn't matter if they're centralized or decentralized. The idea is to buy on one exchange and sell on the other one if the price is different. For example, if you can buy an Ether or a Bitcoin on one exchange with 5,000, and the price for the same asset on the second exchange is 6,000. You can buy on the first one, sell on the second one, and you'll have 1,000 as a profit. This is called arbitrage. Moving on, an effect of the decentralized exchanges is that usually in the centralized exchange model, you would have basically bots that would connect to the exchange API and send trades and would pull data. But in the decentralized model, all we have to do is actually watch the Mempool. The Mempool is a place where all the transactions that haven't been mined yet are located. So all the node operators have this memory of pending transactions that they would choose and put in a certain order and then mine. And for example, in this block, we have 135 transactions, and you can see that that there is a specific order. There is a specific order of the transactions in this block, and depending on which mined first and the second, the price on an exchange might have been different. For example, if and what happens is that people would write bots, arbitrage bots, that would monitor price on different decentralized exchanges. And when they would see a profit, they would send a transaction to make the deal. If instead there are big transactions in the Manpool, and you monitor for them, and you see that someone wants to exchange, for example, $1 million into Ether, you could actually go to Uniswap and perform a trade before that, knowing that the price after the $1 million transaction would move in a certain direction. And by this, you can gain some money because you would be able to make a transaction afterwards in a different direction. So you can buy, and then there will be the $1 million transaction that would buy a lot. The price would go up, and after that transaction, you would sell. And this is called a sandwich attack, where actually it's not an attack; it's just a front running. But there are bots that monitor the Mempool and try to perform a sandwich attack that would imply that they would move the price a lot before your trade, and in order for you to have a bad trade. And that is called the sandwich transaction. And I think it would be better explained by this image. And credits for this image go to Degen's partner on Twitter. Okay, moving on. And a new concept that appeared, I think, last year, but it got gained popularity this year, was the term flash loans. Basically, all this interaction with the exchanges requires that you'd have some money. And having some money would allow you to go exchange some Ethereum for USDC, and then exchange this for something else, and so on. But if you don't have money and want to perform a trade, you can now apply for a flash loan. A flash loan is just a contract that would send you some money, and after would let you would call your contract, and you'd be able to do everything, whatever you want with that money. In this example, go wild, they called it. And after your transaction, you should repay the loan, send back the money, plus some small fee, some interest, in order for everyone to be happy. So basically, you would only need to pay the gas fees in order to profit of any amount of money that you would like. And the concept of flash loans opened a lot of opportunities for hacks. And that's what happened in the BZX hack number 1 and number 2 that happened in February this year. Basically, the attacker loaned 10,000 Ether and then performed a trade with some leverage. Because he had a lot of money, he was able to change the price dramatically, and because he had the 5 times leverage order on that asset, he afterwards was able to win a lot of money from this trade. So flash loans basically mean that you can do trades with millions while you don't actually have the money. And the smart contract code of the flash loan takes care that it will revert in case you don't repay the loan plus interest at the end. Basically, they have a function, loan, that would send you the money, call your function, and after calling your function, they will check their balance and make sure that you paid. If not, they will revert the whole transaction, and nothing happened in that case. No money moves. Okay. So last thing that I want to talk about, and this will be like literally 2 minutes, is that lately there are a lot of bots that do front running and Mempool analysis and that actually are quite smart. They analyze the Mempool. For example, if you want to withdraw some money from a contract and you send your address as a parameter, but anyone can do that, they will see your transaction in the Mempool. They will attempt to modify it, put their address, and if the simulation of that transaction is profitable for them, they will send the transaction with a higher gas so that the miners will mine their transaction before yours. And that's a story that happened and was posted by Dan Robinson, and I highly recommend this read. Might be a bit, I don't think it will be too technical, so it explains very well what happens and gives you an overview of everything that happens in this space called Mempool. Okay, so having all this said, I'm happy to get questions from you guys. Thank you.